Good morning, everybody. Unfortunately, Vlad Sabaka could not be here. My name is George Tarnofsky. I'm here to present reverse engineering using X-rays. This is X-ray, not hex-ray. So this is about hardware, not software, okay? Yeah. Okay, very good. So circuit boards come in various shapes and sizes. Please be patient with me. Everybody has seen circuit boards. I know that. But nevertheless, what's not evident is the construction within the circuit board. Here we have, outwardly they all look the same, but inwardly you can see that some of them have multiple layers, some have plain layers which actually obstruct the view where you're not able to see anything within the device with standard methods. So the complexity gets complicated. Common methods used for reverse engineering circuit boards: backlighting, conductive tracing, and mechanical delayering. Backlighting is effective on simple two-layer boards, single-layer boards, and boards without plane layers that actually obstruct your entire view. Conductive tracing works well with some boards, but it's difficult at best. And mechanical delayering is a very messy and destructive method. It can be done, but again, it's very difficult to do. So, okay, backlighting. You can see that in backlighting, a simple two-layer board, the green board up at the top, is easy to see. However, the two at the bottom, you can see that there's absolutely nothing that can be seen because of the two, well, they both have plane layers within the board. A word of caution about what I'm going to be talking about, which is X-rays. Obviously, when you go to the dentist, you see how the technician covers you and runs away and pushes the button and then comes back and sees if you're still alive. Okay, so my point is this: X-rays are dangerous. However, there are some fallacies. Today's equipment is really well protected. Actually, you're well protected. Obviously, this is a picture of me before, I started X-rays. So you can see what happens now. It's not me too. So anyway, okay. So X-rays, you see everything. It reveals everything. There's absolutely nothing that can be hidden. And I'll show you a case where somebody thought they could hide something by using lead, and even Superman doesn't work. Anyway, okay. So here's two decapsulated dies, compliments of Chris Tarnofsky, semiconductor gurus. These are done with his with his microscope. He decapped them, and you can clearly see, specifically the one on the right, that particular device. Seeing it through a microscope, you can see all these details. However, looking at it through an X-ray, it's a poor job of stitching, my fault, but nevertheless, it's stitched together, and you can see that there's nothing, you can't see any of the details, but you do get to see the bonding wires, and you get to see the pads. So this is a live view, what I'm going to show you now. Up to this point, most of you have seen X-rays, and they're still pictures. The beauty of this particular instrument is that it gives you a live view. So, oh, come on now. Seriously? Bear with me. I can't use my pen. Okay, so here's a live view. So even though the signal to noise isn't that good, it's because the sampling rate is reduced so that you can do a live view. But when you find the spot you want to focus on, now you can do the averaging, and it cleans up and you can clearly see. So there you are. So here's another live view. This is a zoom feature, and this is amazing because this you can see down to 5 microns resolution. So it's pretty impressive. So those wires that you see crisscrossing, those are the actual bond wires within the device. So it may appear as though you have disconnects. You have wires. I can't point to them. Where are they? There. You've got this wire here that looks like it's disconnected, and that wire there it's disconnected. But in reality, they're going to those 2 buses. So you can see that they look like they're shorting out. Also, they're not. They're well spaced. So this is a live trace. This is actually, we had to trace out this pin right here. So this is how you would do it if you were to do a reverse engineer on something, or for that matter, have to attack in this mode. So we're going to trace that second one in from the pin 1. So just follow it. And up to this point, it all looks like it's a single dimension. And I'll show you how we can change that, but not in this slide. This slide will just continue to trace. So here it gets a little convoluted. So I increase the sampling rate so I can get better clarity and move along. I'm getting paid by the hour, so it doesn't matter. So I'm getting close to where it's going to be destinated. But see, there's right above that via, almost in the center. It's in there, but if you look at that, it looks very, very, well, complicated. You can't tell which one of these is actually the lead that we were tracing. So you zoom in a little bit, forgive it, just to separate it a little more. You get a good idea. Now it's evident. Okay, so you can see where it went. Went over, down, across, and down, and then over, continued over. So it goes through the BGA. And here you can see the bond wires. You can see the edge of the die, but we don't care about that because we're going after this one lead. And okay, so there's the via, and it goes up to there, and that's it. So that was a live trace, and you can see the clarity. I mean, everything is shown. Or can you see the clarity? Yes, you can. Okay. All right. So reverse engineering becomes very, very easy with this, and this is another case where we had to find data lines so we could talk to this, verify them. We knew exactly where they were once we X-rayed, which was really great. Okay, so the spheres are 24 thousandths of an inch. You can see, again, everything's clear. The reason why this appears to be somewhat mixed up, where you've got vias on top of vias sitting next to them, you're looking at a BGA. The BGA platform itself is a ball grid array platform. The base is a PC board. So you're looking through that PC board, and you're looking through the actual PC board that it's mounted on top of. So you've got a lot going on there, but you can see the vias, and these vias, by the way, incidentally, large ones are 8 thousandths of an inch. So with Nathan, that's about the size of most of your hairs. So you can see it fit right through there, but the other ones are that much smaller. So it's interesting that they can work with feature sizes like that. So here's a direct view. We've been looking at the direct views. Now we have an angular displacement. And at that point, you can see that they're positioned at different layers. And now you can trace out that specific layer. So to the right, if you look at the view, you can see, for instance, this one here, you can see the lead that's coming off is at a different level than this one here, So this is top layer, second, third, maybe fourth or fifth layer of the board. So it gives you an opportunity to trace through and see the rest of it. Yeah, here we go. Okay, so this is a very nice feature that this machine has, and you can do a live tilt. So what we're looking at is to the right. You see these three vias to the right, and you see that trace there. We want to know which one's going where. So now it's easy to see which one goes where. So as compared to when they were on top of each other, it was virtually impossible to tell where they were going to go or where they were going. Okay, so here's a board. This is the board on the left. There's virtually nothing you can see because what they did was they put a plane layer on top, covering the entire board. So all the traces are internal, or majority of them. So to the right, you can see that they're everywhere. Easy to tell, easy to see, easy to touch if you had to by drilling, and knowing what you're going to affect when you drill, which is another slide. Here's a couple of methods that were used to obscure views by some people in some business. Anyway, to the top left, they used epoxy, the same epoxy that the board is made out of. So if you try to dissolve the epoxy, you're going to dissolve the board as well. So with X-rays, you can see right through it. This other one was kind of interesting because they actually hid a, they put epoxy on top of the board, but underneath it, they actually hit the contact area and the chip out of a smart card, pretending that they invented something. That was kind of neat. Anyway. Okay, so lead sheathing. Here's another method of obstructing the view, putting lead in. Well, you know, here's the same view using an X-ray. You can still see through it. It's obscured, but you can see it. More power will take care of that. So here's here's a rad-hardened device to the right side. Looking at it, I'm sorry, left side you're looking right through it, not a problem. But to the right side, you can see the rad-hardened device is obscured pretty well. That again, you can see with an X-ray and go through it. And for failure analysis, which is really why the machine is around, this is the picture to the left. Top left has a missing ball. So this was placed, and there's one ball missing. I think everybody can see that up there. The others are shorts that happen. Remember, solder flows. And if you put enough flux in there, it'll short out, and that's what happened there. And the top one is actually a pretty bad one, where they just because of surface tension, it'll adhere to the next one. So then there you have it. Just like if you're soldering a pipe. Okay, so here's this is an FPGA board with a flash. It's got internal flash within the device, and this particular one we could not get access to. There was one we couldn't program it. So the TDI pin, this is our software that we use. The JTAG was not found because the TDI pin was not connected. So there's TDI. How are we going to get to that? Well, we couldn't get to that via because it wasn't connected to the via, but we can get to the ball. So we took a pin vise. Now that we have an X-ray, we know exactly where we want to go. We have a pin vise. We manually drill a hole carefully until we saw some metal coming out. We knew we were touching the ball. We don't want to drill through the device, right? And we took a pin, and we held it up to that particular ball carefully, and there it was. So we were able to identify the device, program it, reflash it, and continue. We didn't really care again. If we had to do it again, we could, but it was just a one-time thing. Well, that's it. Any questions? All right. Do we have questions? Ah, there's a question. Okay.
You're not on the program. What was your name again?
Why? No, it's George Tarnowski.
And are you related to Chris Tarnowski? I honestly don't know. I'm asking.
Oh, yeah, he's my son.
Okay. Is he here, actually?
He's not here, unfortunately. Okay. Yeah.
Anyway, I saw one of his talks at DEF CON a few years ago.
Yes.
And it's one of my favorite talks. I still remember it. So say hi to him for me and us. And
I certainly will. Okay.
I remember thinking at the time, like, Chris, your talk is amazing. How did you get into all this stuff? And I think you explained.
I did have some responsibility in that.
But, I'm sure he was soldering at a young age. So.
Oh, absolutely. Oh, yeah. We did a lot of work together in the young age.
Thank you very much.
Thank you. And we have some questions. Okay. How are we doing time-wise?
What machine are you using for X-rays?
It's a Glenbrook Technologies. Thank you for asking. I should have added something about that in this talk. It's a relatively inexpensive machine. They're in New Jersey, and it's about, depending on which one, you can go up to $90,000. But it is a very safe machine, and that's what I like about it. And the resolution is pretty good, and it's reliable. So.
Have you had any issues with like flipping bits and flash because you've been exposing it to X-rays?
Not at all. Never, 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 Not one time. I've heard this so many times. Not one time has that happened.
Okay, and one more. Are you normally just trying to trace out one particular connection, like with the JTAG example, or have you ever been given a board and been told, we need you to come up with a net list?
Yes. Yes, I have. Yes, I have. And it's a lengthy process because you can see what you have to do.
You do it by hand or?
Yeah, it's completely, the machine is completely manual.
Right.
Yes.
So I'm really curious how this compares to fib-sem reversing. Is there an advantage to X-rays versus the?
Well, they're completely two different areas. You can't do PC boards with a SEM. You can't do the chips with an X-ray. But you can, if you have both, you've really got quite a nice little business going. Which, by the way, Chris does have a fib and a SEM.
So if you could automate the stepping on the machine, do you think that,
Step and repeat, yeah, you could do, and a lot of them do. We've tried, but honestly, we don't, to have a repeat order to check, or for that matter, to do a complete board and panelize it. The problem is you're going to have to do that third dimension as well. You're going to have to flip it because you're not going to know what layer things are lying on.
is that one of the stepper controls, is the angle?
Yeah, you would need one for that as well. But again, though, you still need to, you have to have human intervention no matter what, because remember, this is only grayscale. So if you're looking at something and it's kind of more gray than something else or darker than something else, there could be something else there at the same gray level or darkness level, so it may think it's on the same PC level, PC board layer, but it's not. So it really takes a human to go through it.
Okay.
And that isn't to say that automating it, you can't take that data and then have the human analyze it, right? So yes, that would help.
Got another one down there.
You're getting your exercise. I can hear you. Oh.
This is actually very cool, but do you know if they're planning to apply any more advanced imaging techniques, computer tomography, things like that, to allow you to get a three-dimensional view out of the machines?
Yes, that requires a step and repeat as well, something that the positions have to be repeatable, so you can rotate. It's very, very tedious because they actually rotate it. They step it, rotate it, and they take the pictures, and then they put it together.
Okay,
So
because like your commercial like hospital CT machine, they actually rotate the X-ray
Oh,
head
yeah,
instead of
yeah.
the piece because, well, people don't like spinning.
Well, that's a little bit different, that subject. Incidentally, that same company that makes this machine, when I went up there to see one of their, they give classes occasionally, they had a rat underneath a new machine that they had, and they had a catheter stuck in the rat, and that was the purpose, so that the operator could actually have the subject there and manipulate the catheter while they're watching it. And there was absolutely no emission within, I would say, an inch of the actual X-ray itself. It was pretty neat. Anyway, in case if you want to do anything like that to a rat. Any other questions? No? All right, well, thank you very much.